Hello everyone, I am Arpa Dastider, and in this video I'm going to give a short demo lecture on one of the most fundamental building blocks of digital electronics, which are latches. So before going into any deeper, first we need to understand why we need them. So in digital systems, not all circuits depend on just the current inputs. Some also need to remember what happened earlier. Those are called sequential circuits. So in a sense, they need to keep memory. So how do we store memory in circuits? The answer starts with latches. These are the simplest way to store a single bit of information, and they store information in two stable states, 0 and 1, and this is why they are called bistable. There are several types of latches. Let us start with the basic SR latch or the set reset latch. So this circuit works based on two cross-coupled NAND gates, which have two inputs, S and R, and two outputs. And the outputs are usually complementary to each other, and this is why they are denoted as Q and Q bar. And these outputs are fed into the NAND gates to make a feedback loop. So to understand the working mechanism of this circuit, first we can denote Q as the NAND operation of S and Q bar. Similarly, Q bar is the NAND operation of R and Q. So there are four possible cases of the inputs. Let us start with this one where S is 0 and R is 1. So the 0 value is fed into the upper NAND gate, which makes Q to be 1, just according to the NAND logic. And that 1 value is then passed to the lower NAND gate, which makes Q bar to be 0. So we find this state, which is called the set state. Then if we look into this condition where S is 1, R is 0, it works just like the previous one. Now Q bar becomes 1 and Q becomes 0. So this makes our second state, which is the reset state. So now let's see what happens when both of the inputs are given 1. So when both of the inputs are 1, this logic follows as Q becomes Q and Q bar becomes Q bar, which means that this state holds the previous state and works like a memory element. And this only happens when Q or Q bar are complemented. So the last case is when both of the inputs are given as 0. So just according to the NAND logics, when S and R both are 0, Q and Q bar both becomes 1. And this is actually quite not according to the condition we learned about earlier, that the outputs need to be complementary. So this case is forbidden in practical uses. To understand its operation more clearly, we can look at the timing diagram. At first, the set state is made and Q thus becomes 1. Then the memory is kept by setting S and R to 1. Then again the reset state, memory, and again the set state. So at time T5, we can see that S and R both are set to 0, and hence the output becomes 1. So the outputs are now 1. And an interesting thing happens at time T6 when both of the inputs are made 1. So just like that, as previous values are 1 and S and R both are now given as 1, this makes the outputs to become 0 immediately. And again, because of being 0, it forces them to be 1 again. So this oscillation continues indefinitely and makes unstable or a meta state. So this is why this input condition is forbidden and should be avoided in practical uses. So in this circuit, we have seen that the output changes whenever the input changes. But what if we want control over that? Well, what if we want to change the outputs just when we want them to? So the solution is the gated SL latch. So in this circuit, we use a clock signal and two extra NAND gates. So what happens here is that when clock is set to 0, both of these points, named S prime and R prime, becomes 1 according to the NAND logic. So this part actually works like just the previous one. So according to that logic, when clock is 0, the output does not change, and hence it works like a memory element. And what happens when clock is given 1? So when clock is given 1, the complemented value of S and R are passed to these points, and rest of the circuit works just like the previous one, only the inputs are now complemented. So this circuit has control over the outputs, but the condition of invalid state or the unstable state still exists here. So to overcome that, the gated D latch comes to the action. So in this circuit, we use only a single input D, and instead of S and R. Here D stands for that. So what happens here is that now the value D and the complementary of D are used instead of S and R. So the condition of S and R both being similar is now gone. So hence the invalid condition is also eliminated here. So in this circuit, the output keeps its value when clock is set to 0, and when clock is set to 1, simply the D value passes to the output. We can see that from this timing diagram also. If you look into the third clock pulse, we can see here that when clock is 1, the output actually follows the changes of the input D. But when clock is turned 0, regardless of the input D, Q holds its previous value. And from this, we can see that the output only changes depending on the clock level. So this is why this circuit is also called level sensitive. So to summarize the whole thing, we have first studied about SR latch, which are the basic storage block of all sequential logic and circuits, but they have a forbidden input condition. Then we have studied about gated SR latch, which uses a clock signal to control the response of output, but still the forbidden or invalid input condition remains here. To overcome that, we have studied about gated D latch, which uses a single input D to eliminate the invalid states, and they are also called level triggered. So that's all. Thank you for your patience.